Hi everyone, so today we are going to look at the line integrals of a vector field. So you can look at the module, okay? So this one is the lectures for our week 12. Okay, we are going to look at the line integrals of vector field. Okay, you can look at page 157 of your module. Okay, so what is line integrals of vector field? So the formula for the line integral of vector field is something like this. Okay, you have the line integral. Okay, the C stands for the line, stands for the curve. And because it is dealing with the vector field, okay, so you won't see the scalar a function anymore, but you will see a vector. Okay, you will see a vector and dot product. Okay, you see there is a dot product with dr. Okay, so the dr here is stands for the line. Okay, the length of the curve. Okay, so for example, let's say if you have your f, okay, equals to the mi plus nj and plus the pk. Okay, because your f is a vectors, and if your r, okay, if your r, okay, r is also a vector, r is also a vector, and if your r is equals to xi, okay, plus yj and plus zk, okay, because you need to perform the differentiations, okay, the differentiation dr, so your dr will become as you differentiate it, okay, plus y differentiate it, and plus the z, okay, you differentiate it. Okay, so now you combine this vector f and this dr, okay, through the dot product. Okay, so the whole line integral function will become mi, okay, plus nj plus pk, okay, and you dot product with s prime, okay, plus y prime j plus z prime k, okay, z prime k. Right, okay, this one is a differentiate. It's a differentiate with respect to the t, okay, dt, okay. So this is the line integral. So what you will do is later you perform a dot product, the line integral will become mx prime, right, plus ny prime plus pz prime and dt. Okay, so you already transform the line integrals of vector field, okay, this is the line integral of vector field, into the line integral of scalar field. This is the line integral of scalar field. Okay, so the process to solve it will be the same like what we have learned previously. Okay, what we have learned previously about how to solve the line integrals of scalar field. And here there is one thing that I want you to take notes. Here I write it as a dt, right? dt. So meaning that you have to convert all into the variable t and dt. You can also convert it into the dx, dy, okay, or dz if it is necessary, okay, dx, dy, okay, so you also can convert it to the dx and dy, okay, no problem, right, so you can look at the procedures on page 157, okay, So they show you the 4 steps in evaluating the line integrals of vector field. Okay, change all the parameters to t, and then find a dr, and find the f dot dr, and then calculate. Okay, so this is exactly like what I had explained just now. Okay, we look at an example in the module. Okay, example, maybe I want to look at the example at the back. Okay, we look at example page 160. Okay, exercise 4G. Okay, that is the exercise 4G. Okay, we look at this example. So question 1a. So you have to evaluate this. Okay, this is the line integral of vector field. Okay, evaluate this. If given you the f is s plus 3y, okay, this is your I, okay, plus 3x plus y, okay, this is your j component, and your r, okay, is in t, okay, so you have a ti, okay, plus t squared j, okay, and your t has been given. Okay, that is from 0 to 1. Okay, so let's do it. So f, we already have it. Okay, very clear what is our f. So about the dr, you need to perform the differentiations. Okay, so with respect to the t, so the dr over dt for this would be 1, okay, plus 2t, okay, j. Okay, so now I want you to take note on this, okay, and something that you must remember. Okay, x equals to xi plus y, y square, no y square, yj, okay, yj. Okay, so this is something that you must remember. Okay, this is always apply for all the line integrals of vector field. Okay, what's the purpose of having this is, okay, we want to find, okay, the relationship between the x, y with the t. Okay, so now you can do comparison between these r and between these r. So from here you can see that, okay, the t, the x is equals to t, okay, and the y, okay, is equals to t squared. Okay, so I will write down here, x equals to t, y equals to t squared. Okay, so what's the purpose of having these two is we want to convert all into the t. Okay, so let's write out. Okay, so you have the x here, so x is going to replace with this, y is going to be replaced with this. Okay, so you have the t plus 3t squared, okay, and this is your I, plus 3t plus t squared. Okay, this is your j. Okay, and you dot product with the dr. Okay, so dr is this one. Okay, we have calculated just now. So you have the I, okay, plus 2j and dt. Okay, so the t is from 0 to 1, right? 0 to 1. Okay, so let's continue. 0 to 1. So I with I, j with j components. Okay, so you get t plus 3t squared. Okay, this is the multiplications of I component, and then you plus with the multiplications of j components. So you have a 6t, okay, plus 2t squared, okay, dt. Okay, so the thing is almost done. Okay, you have converted into the line integral scalar field, right, which has only one variable t. Okay, so you can simplify. This will become 7t, okay, and plus 5 t squared. Okay, so you can press your calculator. So let's press the calculator. So we have integrate 7x plus 5x squared, okay, so 1 here, 0 is here. So you get 5.17. Oh, it's not. Answer is 4. 7x by 5x squared, 0 to 1. The answer is 4. Did I make any mistake? Let me double check. Okay, let me double check. We have the t. Alright. I missed the t here. Okay, I missed the t here. Okay, it should be 2t. Okay, so yeah, this thing is wrong, right? The way I'm doing this thing. Okay, so I do it again. Okay, so this would be 6t squared, okay, and plus 2t cubed, yes, and dt. Okay, I think will be correct. So you will have the t plus 90 and plus the 2t cubed and dt. Okay, so the answer should be equals to 4. Okay, answer should be equals to 4. So this is how you perform the line integrals of vector field. Okay, so class, when you actually perform the line integrals of vector field, you are actually finding the work done. Okay, this term actually represents the work done. Okay, the work, okay, done by the force. Okay, done by the force to move it, to move. Okay, to move for example, a components or a particle of a particle along the curve C. Along the curve C. Okay, so you can move the particle along different type of C. Okay, so different type of C might give you different work done. But if, okay, the work done, okay, that is that you get from different path is the same. Okay, so we said that the force is conservative. We say that the force is conservative. So this one is I want you to look at the page 161. Okay, conservative force field. Okay, so this is what I'm going to show you, okay, about how to know that the force, okay, or the field, okay, the vector field is conservative. So you look at the example 4.24. Okay, so you have to find the work done. So like I mentioned, the work done is actually you solving the line integrals of vector field. So the answer here will be the work done. Okay, so find the work done by the force field, by the force, this one. Okay, but then when the particle move from 0, 0 to 2, 4, using different path and different curve, quite similarly like the line integrals of scalar field. Okay, so you have three options, three curve. Okay, we look at the curve 1. Okay, the curve 1 is a straight line. Okay, you can see from the diagram it's a straight line. Okay, so it's a straight line, something like this. Okay, joining the 0, 0 and also the 2, 4. Okay, they give you the straight line equations already. Okay, so let's solve for the line integrals of vector field. So it is solved by converting R into the T. Okay, but in fact you can convert it into the X, okay, and also the Y. Okay, just like the line integrals of the scalar field. Okay, so now what we have to do is we look at our R. Okay, because we are clear about our F already, right? So remember I told you you must always remember your X is equals to this. Okay, right, so here I would like to convert it into the X or dx. Okay, so according to this one, I think it will be easier if I convert the line integrals into X. So here I make it to be dx. Okay, so here will be I. Okay, will be I, and this one will be 0, right? Because there is no X components, so you have a 0 J component. Okay, so your dr will be equals to I, okay, and dx. Okay, so y will be equals to 2x. Okay, look, now I put them together. Okay, so the f is xi plus yj. Okay, and dot product with the dr over here. So the dr only has the I component, so I will do it this way. Okay, so it will become x dx. So now when you want to calculate this line integral, you just need to refer to the x. Okay, so the x is changing from 0 to 2. Okay, right, 0 to 2. Okay, so you can start to calculate this thing. 0 to 2. Will it be the same? Seems I won't be the same. Okay, great. Oh no, sorry. I missed again the y. I didn't convert it. But even though I convert it, it will be 0. So this y, if I convert it, it will be 0. So let me try first. Oh, the answer is equals to 2. Oh, yo. I missed one step again, I'm sorry. Regarding this part, I missed one step again. So this one. Sorry, I missed one step. So this is y, right? So you have to convert it into the 2x. Okay, sorry. 2x is here. Okay, 2x is here. So you get 2j. Okay, 2j. Okay, so it will be I plus 2j dx. I plus 2j dx. Okay, so it will be x. Also in this case, here it will be 2x. Okay, 2x. I plus 4x, right? S plus 4x, okay, x plus 4x dx. Okay, so this one will be the same like what is in your module. Okay, they convert it into the t, but you convert it into the x. So you get your work done is equals to 10. Okay, this is your work done. And for the second part, okay, the second part is a curve. Y equals to x squared. So it is a quadratic curve. Okay, so that quadratic curve will be joining this 0, 0 and this 2, 4. Okay, quadratic curve. Okay, so we will use a similar method. Okay, similar method. Okay, so I will going to convert it into the x as well because it is easier. Okay, so my my r will be this thing again. Okay, what is this thing? This is something you have to remember. Okay, the r is always this one. It is always this one. Okay, so you must remember that. Okay, you must remember. Okay, so now we convert it as I, and the y is the x squared j. Okay, x squared j, you convert all the y into the x. Now is the dr. Okay, so dr equals to I plus 2x. Okay, same like the previous one. No, same like the previous one. 2x. All right, j. Okay, just now is x, now is 2x. Okay, so now put it inside the line integrals. So you have I write in this way so that I don't need to write the I and j component. X and y, this is the vector. This is a vector, it's not a coordinate. Please, this is the vector. Okay, a vector. I write in this way using the this bracket. Okay, and then 1, 2x. Okay, and this one I have the dx. Because I differentiate with respect to the x. Okay, so the x still is from 0 to 2. Come x. Alright, I forget to convert again. So this is the x squared. Right. So how you do it is the I component multiply with the I component and j component multiply with the j component. Okay? Right, so and plus 2x cubed. Okay, 2x cubed. Okay, so you can calculate this thing. Okay, you can calculate this thing. which is also equals to 10. The work done is also equals to 10, meaning that, okay, if the force, okay, push the particle from this point to this point by going through, okay, the curve, something like this, okay, the work done will be equals to 10. Okay, for the previous one is it push the particle from this point to this point using a straight curve, straight path. Okay, the work done is also equals to 10. Okay, right. Okay, they have the same work done. But let's try the last one, path C. So path C is right. It break it into the piecewise, right? C. Okay, the path C3 will be from 0, 0 to 0, 4. And right, this is the path C1. Okay, and then from 0, 4 to 2, 4. C2. Okay, so for the C1, it's very clear that the x is 0. Okay, and for the C2, the y is 0. Right, you can write down the x is 0, the y is 4. Okay, y is 4. So you use the piecewise technique. Okay, very similar. We look at the C1 first. C1. Okay, so R equals to x plus y. Okay, this is always the same, always the same. Okay, so we look at path C1. Okay, so here the x is equals to 0, so we replace the x with the 0, right? So we cannot do the dr dx, we can only do the dr dy. Okay, dr dy, which is equals to j. Okay, so we look at the line integral. So you have the x and y, and you dot product with the 0, 1, 0, 1 dy. Okay, so the x is 0, so it will be y dy left. Okay, y dy, and the y, yeah, you can see is changing from 0 to 4. 0 to 4. Okay, so you can calculate what will be the answer. Okay, 0 to 4. Okay, it is equals to 8, right? So this is for the path, or in your module is labeling path C3. Yeah? So to avoid confusions, I will change it to C3 lah. Okay, C3, C4, and this is C3. Yeah? Okay, so we get 8. Okay, so for the piecewise curve, you have to add the path C3 and path C4 together. Okay, so you have to do for the C4. So repeat the same step. R equals to x, okay, plus y, right? So the dr would be, okay, let's see what happens. So for the path C4 is here, the y equals to 4. Okay, y equals to 4, right? Okay, no, sorry. The y equals to 4, okay? This is equals to 4. So you can only perform the dr dx. So you get 1i and 0j. Okay, so put in the line integral. You have the x, I, y, j, dot product with the 1 and 0, and this is dx. This dx is when you multiply up. Okay, so the dx will be here. Okay, right, so now not yet complete. The y, you have to replace it with the 4. Okay, So regarding the interval, you can refer here, for the x interval is from 0 to 2, okay, 0 to 2, so you get x dx. Okay, you get the x dx, so it is equals to 2. Okay, so summations of a C3 and the C4 will be equals to 8 plus 2, which is 10. So again, it is 10. So can you see when you perform the line integrals of vector field using different paths, okay? You have so many paths, okay, C1, C2, C3, C4, okay? You will get the same work done, okay? You will get the same work done. It means that it is independent, okay? The line integral of the vector field is independent of the path. Independent of the path, it means that it don't care what path that you are choosing. Okay, so if you found that the line integral, okay, is independent of the path, okay, independent of the path, then the f, okay, this is the force, is conservative. Is conservative. Okay, is conservative. So for all the conservative field, okay, conservative field, okay, there will be a scalar functions, okay, and if we find the gradients of the scalar functions, it will be equals to the f. Okay, what I means that if is the f, okay, this f, okay, can be represented by gradients of these scalar functions. Okay, remember, this is what you have learned previously. This is a gradient. No, this is a del. But if you do it in this way, this is a gradient, okay, of a scalar functions. Okay, right. So I repeat. Okay, if the line integral is independent of the path, the f is conservative. Okay, so when it is conservative, there will be a scalar functions, and if you find the gradient of this scalar function, it will be equivalent, okay, to the vector field, vector field f, okay, or the force. Okay, so when the f, okay, we say that it's a vector field or it is a force, okay, is conservative, it means that when it is conservative, it means that, okay, the curl of this vector field will be equals to 0. Okay, the curl of the vector field will be equals to 0. Okay, so when this is I introduce you the scalar function here and this one because there is an alternate technique for you to find the work done. Okay, you can refer to page 164 of your module. We look at the example 4.25. Okay, so this is to find the work done as well by using different technique. Okay, so you have been given the force, okay, this is a vector field equals to xi plus yj, okay, so you have to show that, okay, the f is conservative by finding a potential function phi which satisfies f equals to this. So you have to find this one, the potential functions. Okay, so if you're able to find the potential functions, you can prove that the f is conservative. Okay, so the first step is, okay, we try to prove that the f is conservative by using this formula. Okay, the curl of the vector. Okay, the curl of a vector. So when we perform the curl of the vectors, we must make sure that it shows it is 0. Okay, so that we can prove that it is conservative. So how to do it? Okay, so you have to use this matrix, right? Alright, so if you prefer to I write in this way, so I will write in this way. Alright, do you remember what is the curl? So curl is this one, right? Okay, so your f is actually only have the I and j component, right? So you have an x, you have the y. So this one will be equals to 0. Okay, so let's see whether it is 0. Okay, whether it is 0. Okay, so the first for the I component, you hide this thing, right? Okay, look at these 4 terms. Okay, so this is going to give it 0. This is also 0. Okay, so you have the 0 I components. Okay, 0 I component. And for the j component, you repeat the same thing. Okay, you hide this one and hide this one. Okay, so this del x might multiply 0, 0. Del z, there is no z component, so it is also equals to 0. And for the k components, okay, for the k component, same thing, you hide these columns. Okay, again, it is still 0. Okay, so this shows that the f is conservative because all is 0. Now we try to find the scalar, potential functions. The potential functions. So the relationship between the f and the potential function is this. The potential function is this one, right? So do you still remember how to perform the gradients? Okay, so the gradient itself is actually del x, all right? You have the I, right? Plus del y, you have the j, and plus the del z, and you have the k. This is the del component. So when you multiply it with the phi, meaning that, okay, you have to multiply the phi inside, right? The phi inside. Okay, you multiply the phi inside. So you have to differentiate it, okay, the phi with respect to the x. Okay, so f has been given by the questions. Questions tell us that f is equals to the xi plus yj. Okay, so now we can do a comparisons, okay, for this I component and j component, right? Because this one is also f, right? Okay, right. So meaning that, okay, the del phi del x is equals to x. Okay, del phi del y equals to y. So what will be the phi? Because you are asked to find the potential function phi. So meaning that you have to integrate the x with respect to the dx. Okay, so this one you have to do it manually. So it will be the x squared over 2. And always you have a constant c, right? When you perform the integrations without the limit, without the interval, you will have a constant c. Okay, so this one also the same thing. Okay, you integrate the y and dy. So you get y squared over 2 plus the c. Plus the c. Okay, now you have two options of the phi, right? Two options of the phi. So which one to be taken? Which one to be taken? Okay, the answer is both. The answer is both, meaning that the phi will be x squared over 2 plus y squared over 2 and plus the c. Okay, so we assume this c and this c combined to be c lah. Okay, just any constant. Okay, any constant. So now we get the potential functions. okay, that is asked in question A. Okay, so you can try putting these potential functions over here. Okay, you can try and you will get this thing. You will get this thing. You can try yourself. Okay, we look at the B. Okay, B is to find the work done based on the potential functions. Okay, you can find the work done based on the potential functions. So we know that, okay, the particle is moving from this point into 2, 4, 0, 0 to 2, 4. So what we have to do is, okay, to find the work done, okay, we have to take the potential functions, and then, okay, for the starting point, we put it here, just like we perform the integrations, right? Okay, so we take the potential functions, okay, when it is at position 2, 4, minus the potential function when it is at the position 0, 0. Okay, so meaning that, okay, all the x will be replaced with 2, so you have a 2 squared over 2, okay, plus 4 squared over 2. Okay, this is represented, this is from this one. Okay, minus, okay, 0 over 2 plus 0 over 2. There is no more c because you have the coordinate already. You have the value for the x and y. So that is no more c. Yeah, you don't need to consider the c anymore. Okay. Right. So you will get your answer equals to 10. Okay, which is the same as the technique that we apply by using the previous technique. Okay, by using the previous technique. All right. So here there is one thing very important that I want you to take note for this one. Okay, for example, okay, I'm saying for example. For example, when you perform the integration with respect to the dx and dy, you found that there is one term that is the same. For example, just example, okay, for example, you get this xy for the integration with respect to the x, and also integration with respect to the y. Because just now I'm saying that you have to take both, combine both to be your final potential function, right? Okay, so you take this one, you take this one. And if here you have the xy, okay, what you have to do is, okay, you insert the xy for only once, even though it appears here and also here. Remember, you can only add it once. Okay, if you make it 2 over here, okay, and you perform again this thing, okay, the gradients, okay, of the potential function, you won't get this one. Okay, so just take once, just take once. Okay, just take once. Okay, and then see. Okay, right, just take once. Understand? You can look at the example 4.26. Okay, this is an example that has this as a components that I mentioned over here. Okay, right. Okay, so I don't want to make the video to be too long, so this is all about the line integrals of a vector field. Let's go through again. Okay, right, the line integral is to find the work done. So you will have the two vector components. Okay, you will have two vector components, that is the f and also the dr. And as I said, you must always remember the r equals to this one. Okay, sometimes you see that I only write the I component and j component because the f only has these two components. That's why I only write these two components. In fact, it can have a z component as well. Okay, right, then you find the differentiation of the dr. Okay, you find the differentiations of the dr, and then you combine them. Okay, this is when you convert it into the dt. Okay, you can also choose not to convert it into the dt. Okay, so next I show you, okay, how to perform the line integral by using different paths. Okay, if the answer that you get from different paths is the same, we said that the force is conservative. Okay, the force is conservative and it is independent of the path. Okay, so when the force is conservative, there will be a scalar function. Okay, there will be a scalar function here. Okay, the gradient of a scalar function will be equals to the f, and also the curl of the f will be 0. This is when the f is conservative. Okay, so we can use this technique, okay, the potential functions, to find the work done also, and this is the procedures. You can refer example 4.25 and 4.26 of the module. Okay, so there are also example, okay, in the exercise behind. Okay, so this is the starting point, and this is the ending point. Okay, just replace the x and y into your gradient, into your potential functions, then you can get it. Okay, so as a homework for you, I want you to submit the handout, okay, of these lectures into the author. Okay, so the submission time will be considered, okay, whether you really watch this video or not. Okay, right, so submit this handout, okay, in the author. Right, thank you, class.